The way we do it today is we use solid fuel in pressurized water, and the water is a great coolant. It's also really, really good at slowing down neutrons. This technology has the ability to be probably the most compact nuclear reactor, and this is why it was originally designed for nuclear submarines, and it's been very successful in nuclear submarines. But if we boil that down just to its absolute core components, a nuclear reactor is a place where some coolant gets heated up, and then that coolant's going to pass out of the reactor into a heat exchanger, and it's going to heat some working fluid, typically water and steam, but maybe gas, as Dr. Forsberg talked about. But basically that's its job. It's going to, there's going to be a primary coolant, it's going to heat a working fluid. That working fluid is going to make electricity, and some of it's going to go out as waste heat. And depending on what we choose as a coolant can have a pretty profound impact on the way the reactor works and its benefits. Another important aspect is the temperature at which the coolant is coming out of the reactor. That makes a really big difference. It helps us determine how much of that energy we're going to be able to convert to electricity, the product we want, or hydrogen, or any other desirable end product. It's driven entirely by the thermodynamics of the process. A guy named Carnot figured out this equation of how much we can convert into useful work, and it's dependent on how high the temperature is. The higher the temperature, the more work we can make out of it. So we have a big incentive to use a coolant that can go to high temperatures, and there have been about four coolant categories that have been investigated for use in nuclear reactors. This is a chart I think we saw a little bit earlier too that has to do with the pressures of these coolants, atmospheric pressure and high pressure, and the temperatures. And ideally what you would want is you'd want a coolant that would run at really low pressure and really high temperature. And that's what these liquid fluoride salts enable. What you wouldn't want would be a coolant that ran at high pressure and low temperature. And unfortunately that's what we have in water-cooled reactors. We have a coolant that has both the undesirable features. So this is really where we want to go. There is something great about water though, is it holds lots and lots of thermal energy. So for a given volume, water can really drink up a lot of energy, and that's good. This determines the size of a reactor. This really kind of is a yardstick. When you use gas, it really can't hold very much, but water can hold a lot. Well, there's something that can hold even more, and that's this fluoride salt. It has an even better volumetric heat capacity than water, and water's is already really, really good. So combining these attractive features together starts moving you in the direction of looking at the fluoride salts. And they also have some other wonderful properties. They're chemically stable in air and water because they're fluorides. They don't want to be something else chemically. They're already kind of at rock bottom chemical stability, and this gives them this remarkable liquid range, 1,000 degrees C of liquid range, where they're not going to undergo a phase change. So although we do have to get them up to about 400 degrees before they melt, they have this just remarkable liquid range after that. So when we want to reduce the cost of building a reactor, we want to make them easier to manufacture, easier to put on the grid, reduce capital costs, we've got to think about how to get things in the reactor to do as much as possible. The water-cooled reactor is a great example of this. Water is doing two things in a water-cooled reactor. It's both cooling the fuel and it's moderating the neutrons. And both of those roles are absolutely essential to the operation of the reactor. With a fluoride salt reactor, we can also get it to do two missions, and one of those is to carry the thermal energy as a coolant out of the core, but in this case it can also hold the fuel because these salts are remarkable solvents. We can dissolve nuclear fuel into them in the form of uranium tetrafluoride. So this is what Flibe salt looks like when we dissolve uranium tetrafluoride into it. It goes from being absolutely transparent in the previous slide to having this kind of slightly green cast to it. That's the dissolved uranium tetrafluoride in there. So in this reactor, Flibe salt can both carry the enthalpy and it can serve as a fuel carrier. And so how does it work? How do we go and use these reactors to make electricity? Well, this has been gone over a couple of times, but we run the salt through the core of the reactor, and in the core, neutrons are slowed down and nuclear reactions take place. Energy is added to the salt, temperature goes up, the salt exits the core and goes through a primary heat exchanger where it gives up this energy to a coolant salt. And this is the coolant that will then carry that energy outside of the reactor's containment boundary to a gas heater. And we foresee using a gas turbine. This is a closed cycle gas turbine, a little bit different than what we saw earlier, but the same basic principle. We're going to heat a gas. The gas is going to go through the turbine, and it's going to drive a shaft, which generates electricity thanks to this generator right here. That gas has to then be cooled, and there's some opportunities for what we can do with the waste heat before passing into a compressor and closing the cycle. So essentially, the energy, which is born in the reactor, passes into the coolant and then into the working fluid, generating the electricity. There's another very important aspect of what you can do when you have salt as both a fuel and a coolant, and that is the use of an important safety feature, which is called the drain tank and the freeze plug. And this is one of these things that if you take a minute, it's not that hard to understand, but when the reactor is operating, you have a little plug of salt in the bottom of the reactor, almost like a drain in a bathtub. And that drain is blocked by this little frozen plug of salt. And the notion is that if you lose all of the power to the reactor and all of the emergency coolant and everything like that, that little plug will thaw. And then the fuel that is in the reactor will drain out of the reactor into a drain tank. And the drain tank's job is just to let the heat that is being generated in that salt be rejected to the environment. So unlike the reactor vessel, which is designed not to leak any heat, the drain tank is designed to just leak heat out into the environment and to allow that fuel to cool down. And this really addresses one of the key concerns about nuclear reactors, which is how do you deal with the removal of decay heat. This remarkable feature was demonstrated as I'll go through, because we actually built one of these machines back in the 1960s. An experiment was conducted at Oak Ridge National Labs called the molten salt reactor experiment, and they manufactured a reactor vessel. It wasn't terribly big. You can get a sense for the size of the reactor vessel. Inside it contained graphite, which was used to slow down the neutrons that were born from the fission reaction, and then the salt was pumped up through the flow channels in the graphite. It's a little hard to see, but there are milled channels in the faces of these graphite rods. So the salt would come into the bottom of the reactor, it would pump through, and then it would be collected at the top. And as it moved through the reactor, it picked up thermal energy. It got hotter. It was very safe and easy to control. I've had the good fortune to talk to some of the people who actually worked on the reactor, and they said, man, it was a really boring job. The reactor just did what we wanted, and it never misbehaved. And so you can see not a terribly extensive control room. It was very simple internal structures. These are not fuel elements, they're just graphite. The fuel was a liquid that pumped up through these graphite elements. This was the reactor. It's a primary heat exchanger. It's pump all in a relatively small volume here. And this is the primary heat exchanger, and a nice 60s looking guy with a skinny tie right next to it. I don't know if I met him or not, but this ran at high temperature, and because it ran at high temperature, it had the potential to generate electricity very efficiently. Now, this particular experiment was not coupled to a gas turbine or a power conversion system. It was meant to demonstrate this so that later on a more extensive system could be put together, and it was operated very, very successfully. 20,000 hours of successful operation from 1965 to 1969. The fellows who worked on it were extremely proud of their accomplishment. It was revolutionary. It still is revolutionary. Unfortunately, in 1972, it's so easy to find unflattering pictures of Richard Nixon on the internet. Unfortunately, in 1972, Richard Nixon decided that due to some changes in priorities and budget cuts, we were going to pull the plug on liquid fluoride reactor research. And so that was the end of that. And time passed, and things changed, and priorities shifted, and now we are more where we are today, which is we're worried about things we weren't so worried about in 1972. We're worried about global warming, we're worried about climate change, we're worried about melting glaciers, we're worried about the effects of air pollution from coal and fossil fuels. We're concerned about the fact that our low-carbon alternatives are diffuse and intermittent and require a lot of resources in order to construct them, and they don't run 24/7. And that leads to the problem of we live in a society that likes to have power 24/7 and relies on constant, reliable energy. So it has become very popular to consider small modular reactors, and we at Flibe Energy are really big fans of small modular reactors. We'd like to build one too. I like to point out that the guys at Oak Ridge were designing small modular reactors back before small modular reactors were cool. This is a 1968 design for a thorium reactor that was to be built in modules. 4 modules coming up to 1,000 megawatts, and it turned thorium into electrical energy. And they had the idea, hey, we're going to build it in a factory, and it's going to have all this reliability, and we'll be able to test it out. So another thing that was really nice about this was because they did not run at high pressure it was a lot easier to manufacture these low pressure components that went into the reactor. You weren't talking about a pressure vessel that had to withstand 2,000 psi. These salts run at essentially atmospheric pressure. And so a lot of pieces of this reactor got much simpler. Another thing too is they didn't need nearly the control rods that a typical reactor needs because they were producing new fuel at the same rate at which it was consumed. They didn't have to overcome excess reactivity. Their reactivity profile was actually very flat through their operating cycle. It was a breeder reactor. It made as much fuel as it consumed. And this is important to think about today because when you want to look at a new reactor, you've got to think about fuel qualification, particularly if you're doing solid fuel reactors. And that's a long and expensive process. One, frankly, that you'd rather not get into if you didn't have to. With liquid fuel, fuel qualification becomes a much easier prospect because you don't expect the fuel to maintain integrity. It is liquid. The integrity is defined by the boundary of the piping in the vessel. And so this can save a lot of time and a lot of money in preparing for a new reactor. We've heard a lot today about gas turbines and their potential to shrink both the size and the capital cost of the equipment that you'd need to build an advanced reactor. You know, this is a slide that was done by a fellow at Sandia Lab showing going from a large steam turbine down to a closed cycle helium turbine all the way down to supercritical CO2. You can realize much greater reductions in size and capital cost. That again facilitates the development of small modular reactors that could be factory constructed, built for lower capital expenditures and put on site more quickly. And what enables this? Well, it's the high temperature. The high temperature is what enables these gas turbines. You know, and there's another aspect to using gas turbines. When we want to go reject the heat, some of these couple very well to desalination systems. And this is something I get really excited about because we hear about the issue with fresh water, what a crisis it will be in the future, how it will be a crisis probably as significant as electrical need. And most reactors, you know, they make the electricity that you could use to drive a reverse osmosis system or other desalination techniques. But with high temperature reactors coupled with gas turbines, you can actually use the waste heat from the reactor, which is more than 50% of the thermal energy, to directly desalinate water. And that lets you do something with a product you're going to throw away anyway. So that's a big, big, big step forward. So just to put this in contrast with light water reactors today, our product is electricity at about 35% efficiency. But if we were to go to these higher temperature reactors, we could produce electrical generation, maybe not quite 50%, more like 45% efficient. And then we could use process heat to produce hydrogen, ammonia, fertilizer, and we could also be using the otherwise waste heat for desalination processes. So there are new opportunities that are enabled by going to high temperature reactors coupled to gas turbines. And they're very exciting for our industrial society because I know a lot of industrial processes want to use hydrogen, they want to use processed chemicals, as we learned earlier. You give the nice lady from the NRL the heat and she can probably make all kinds of things for you. So we formed our company, Flibe Energy, about 2.5 years ago in order to further develop this liquid fluoride reactor technology. We looked around and it just really wasn't happening and we wanted it to, so we went off and decided to do it. And our goal is, you know, we have a small goal to supply the world with affordable energy, water, and fuel. No problem, it'll take about 100 years, but you know, should be worth it. There was a vision that was advanced back in the day at Oak Ridge National Labs, and it was a vision of a sustainable, prosperous future that was going to be enabled through abundant electricity, desalinated water, particularly in places like the Middle East that were riven by conflict and could be put on a different economic basis based on this technology. Alvin Weinberg had a dream that we would end war as we know it by creating agricultural societies and otherwise desert locations. And this would be made possible through the energy from thorium and also through the generation of desalinated water. I still subscribe to this dream. I hope we see it happen. We're going to talk a little bit about how we fuel these reactors. I've talked a bit about thorium and I'll go through this. Thorium and uranium were created billions of years ago in the death throes of a supernova, along with all the other elements that make up our world. But unlike the other elements, they were infused with nuclear energy at that moment that has been retained in their nuclear structure for billions of years to this day, till some creature on Earth could get smart enough to figure out E equals mc squared and the nature of matter as we know it and figure out how to unlock this cosmic treasure that's been waiting for us. So this is what nature has delivered up to us 5 billion years later. 3 things. The single isotope of uranium, or thorium, thorium-232, and the 2 isotopes of uranium, uranium-238 and uranium-235. Now of these 3 nuclides, only one of them is naturally fissile. In other words, you can hit it with a neutron, it will fission, and that's uranium-235, that little red sliver. That's what we use today there's not nearly as much of that as there is of the rest of uranium and all of thorium, but it's the easiest to use, and thus far that's the path we've taken. And these three materials define three possibilities. Uranium-235 burner, which is essentially what all of our nuclear power is right now, or potentially going to the fast breeder reactor to use the rest of that uranium, or to use thorium in what's called a thermal breeder reactor, and that's what this liquid fluoride reactor is an example of. It is also an example of a thorium thermal breeder reactor. Now today's reactors, and let me try to make this chart make a little more sense, they only use about half of 1% of the energy that's in the uranium. And this is a cutaway of fresh fuel in a reactor. And I have prefaced by saying, this only represents about 1/6 of the uranium that went into the process of making this, because 5 parts out of 6 are lost in enrichment. So this has already been whacked down by a factor of 6. And then of this, we only use a small fraction of that in the course of operating a reactor. Well, why is this? Is it because we're dumb and we don't want to use more uranium? No, it's because there are basic limitations on how much energy we can extract from uranium in the kinds of reactors we have today. And they have to do with, forgive me for a little bit of nuclear physics here, but they have to do with how you can turn uranium-238 into new fuel. Uranium-238, if you strike it with a neutron and let it decay a little while, it will decay into plutonium-239. If you strike that with a neutron and fission it, the net effect will be less than 2 neutrons. And you need 2 neutrons to make this happen. So this is why we can only make a certain amount of additional plutonium in our thermal water-cooled reactors of today. They'll make some, but they won't make more than they burned up. Thorium, on the other hand, is different. If you strike thorium with a neutron, let it decay, it will become uranium-233. If that is struck with a neutron, it'll fission, and the net effect will be more than 2 neutrons. If you don't remember anything else from this talk, remember 2.3, because that's the most important number in my talk. It's what makes it possible to continue using thorium in a thermal spectrum reactor. And that fundamentally is the really big deal of thorium. It's not that it's 3 times more abundant, it's not that we can get it for free from rare earth mining, it's the fact that it can sustainably be used in a thermal spectrum reactor. It is unique that way. There is no other material that will do that. If we want to use uranium, the rest of the energy of uranium, we have to go to fast breeder reactors, and that's why you see a fast neutron here. When you go to fast breeder reactors, you get more than 2 neutrons out of uranium. This has traditionally been the interest in the fast breeder reactor, which has attracted many, many, many billions of dollars of investment in the United States. We still don't have commercial fast breeder reactors, but there continues to be a great deal of interest. You don't need to have a fast breeder reactor to realize the energies of thorium. You can do it in a thermal reactor. Well, why does that matter? Well, it matters because to a thermal neutron, plutonium is pretty big. So imagine you're a thermal neutron. That's how big plutonium looks to you. If you hit the blue part, you're going to get a fission. If you hit the red part, it's just going to absorb it. If you're a fast neutron, on the other hand, each plutonium looks a whole lot smaller to you. And these 2 images are actually to scale. So the relative equivalence between a single atom of plutonium into a thermal neutron versus almost 700 atoms of plutonium to a fast neutron. You need lots more fuel in your reactor to make a fast reactor work. And so, big advantage to the thermal reactor. You'd much rather have less fuel. You're also worried that something might slow down the neutrons in your fast reactor and start making each of these little circles get bigger and bigger and bigger, like that one. That's not good. That's a bad day. So you don't want any inadvertent thermalization in your fast reactor. So we like thermal reactors because they can be built in their most reactor configuration. Anything that will change the reactor will make it less likely to go, not more likely to go. And that's a real, as an engineer, I always like putting the marble on the bottom of the bowl instead of at the top of the hill. So the central advantage of thorium as a nuclear fuel is its unique ability to be sustainably consumed in a thermal spectrum reactor. I labored over that phrase, so forgive me for all the adjectives and prepositional phrases in that, but it's an attempt to be absolutely accurate. Again, here's how thorium works. We strike it with a neutron, it becomes thorium-233, it decays to protactinium-233. Over the course of about a month, that will decay to uranium-233. We hit that with 1 more neutron, and it will produce more than 2 neutrons. It's that more than 2 that really matters. This is what makes thorium a special fuel, its ability to be sustainably consumed in a thermal spectrum. What does this mean? Why should you care? Well, let's imagine that we've taken a typical cubic meter of Earth from anywhere on this planet, doesn't matter. This is average crustal abundance of Earth. Inside that typical cubic meter is approximately 2 cubic centimeters of thorium and 1/2 cubic centimeter of uranium. anywhere in the planet. If you were to use that thorium in a fluoride reactor at high efficiency, the energy equivalent of that thorium would be as if you had 30 cubic meters of crude oil. So what this technology does is it creates an energy resource out of worthless, common earth crust. So everywhere on the planet becomes an energy resource better than the highest quality anthracite coal or the highest quality crude oil. Anywhere. This is the end of our worry about resources. Because now all of a sudden our entire planet is a potential energy mine. If this sounds fantastic to you, it was to me, feel free to repeat the calculations. It really works. So, end of the energy crisis forever. As somebody pointed out to me earlier, this will even outlast the sun because we have more thorium on Earth than we'll consume before the sun will turn red giant. So, this is a really, really, really sustainable approach to our energy needs. The technology for this was figured out before I was even born. We are trying now to advance it. It's not as if we don't have some really easy thorium to get our hands on though, because about 50 years ago, the Department of Defense stockpiled 5,000 tons of thorium, and about 8 years ago, the Department of Energy decided, let's throw it away. So they put it in these brand new tractor trailers in barrels, and they took it out and buried it in 12 feet of dirt in Nevada. So the best thorium mine in the world is sitting under 12 feet of dirt in Nevada. There's about 5,000 tons of thorium there. That'll run North America for about 4 years. So if you ever want some, that's the easiest place to go get it. If we don't want to go get that, there's plenty of other places to look too. Let's talk a little bit about nuclear waste, particularly long-lived transuranic nuclear waste. The way we do nuclear today is producing plutonium, americium, curium, neptunium, long-lived transuranic waste that drives the creation of places like Yucca Mountain. This is what you have to worry about over the 10,000 year time frame, not in the near term. How does it make that? Well, it's because uranium-238, which is what most of our nuclear fuel is only one step away from becoming a transuranic. So this is 97% of our fuel, and it forms this plutonium. On the other hand, when you start with thorium, your very first step is uranium-233, which is your first fuel. 90% of that will fission. Then the 10% that's left will go to uranium-234. It'll absorb another neutron to uranium-235, and that's 85% of that will fission. So now you're down to 1.5% of what you started with before you can get to your first transuranic element, which is neptunium. Neptunium-237. And even this stuff isn't that bad because at NASA we take this and we put it in a reactor and we turn it into plutonium-238 for space batteries, which we are in desperate need of right now because we just sent all of our load of plutonium to Mars in the form of the Curiosity rover. Now it's doing great work on Mars, but the bad news is we're out. So we need some of this special, and this is not the regular stuff that we've got tons and tons and tons of. This is really, really, really special plutonium, ironically made very effectively in this cycle. Okay, so what's the opportunity? Why are we having this conversation or talking about this right now? Is because this technology has the potential to generate some very inexpensive energy. The fuel cost is trivial because of the abundance of thorium. We don't make carbon dioxide. We have the potential for very high availability. This is an intermittent source. This is a baseload source like other nuclear reactors. But it has inherent and very simple safety features. And I think this is where we can make a big difference on the cost of it. Why does nuclear cost so much now? We have a lot of engineered safety into the system. And I certainly admired the talk by BMW earlier where they showed how they had taken so many of the potential accidents and designed them out. That's exactly the kind of thinking you want to do. You want to go and say, how can I simplify and make everything safer? And then also this technology, because of the low pressure, is broadly scalable. We can make them large, we can make them small. They're not nearly as sensitive to scaling as high pressure systems are. We all know we're under a lot of political pressure to reduce CO2 emissions, to lower the cost of energy. These two goals tend to be absolutely orthogonal to one another. The public doesn't care, the public just wants stuff. It wants us to keep the lights on, but it also wants us to do something about our waste problem from existing reactors. We watched the movie last night and realized it wasn't all that bad. But it is definitely something that is in the public's mind, and this technology has the potential to do this. So I believe all of these aspects point to this liquid fluoride reactor technology coupled with the thorium fuel cycle as a global energy solution. I want to end with a quote from Alvin Weinberg, who was the director of Oak Ridge National Labs during the time that this research was going on. In his autobiography, he wrote, "During my life, I have witnessed extraordinary feats of human ingenuity. I believe that this struggling ingenuity will be equal to the task of creating the second nuclear era," which is what he called this new era of better and more advanced nuclear technology. My only regret is I will not be there to witness its success. Thank you very much.
Anyone else?